Good morning. We're going to start exponential functions this morning. And the first thing I want to show you is what is the form of a basic or parent function of an exponential function. And that is this right here, y equals a times b to the x power. And here's the one thing that you need to keep in mind. B needs to be a positive number and it cannot be 1. It can be between 0 and 1 or it can be greater than 1. And we're going to talk about graphing these. So the first thing I'm going to do is show you one possible function, and that is y equals 2 to the x power. And the way that we're going to graph this, because we don't know yet what this looks like because we're learning, we're going to make a table of values. So what I've set up here below is a table of values, and I chose some x values. I chose these because I know what to choose, and you're going to kind of get the hang of it. Usually these 5 values are really good for exponential functions, and we're going to graph this. You can see when x is negative 2, y is 2 to the negative 2 power, which is 1 over 2 squared, which is 1/4. So negative 2 1/4, and on our graph, it's way down here. When x is negative 1, y is 2 to the negative 1 power, which is 1/2, and maybe right about there on our graph. When x is 0, y is 2 to the 0 power, which is 1. So that's going to be our y-intercept right there. When x is 1, y is 2 to the 1 power, which is 2, right there. And when x is 2, y is 2 squared, which is 4. And you can see this is going to go up really fast because if you think about when x is 3, it's 2 to the 3rd power, which is 8. So if I go to graph this, it's going to look like this. And these, as you go further and further into the negative numbers, those y values are going to be smaller and smaller fractions, but it is never going to touch the x-axis. It'll never get down to 0. It'll get pretty close, but it'll never get down to 0. Now, this is how you should do these problems here when they're assigned from your homework. The next example that I'm going to graph is y equals 1/2 to the x power. And again, we're going to use a table of values. And again, I'll choose negative 2, negative 1, 0, 1, and 2. And you can see if x is negative 2, I have 1/2 to the negative 2 power, which, flip it over, is 2 squared, which gives me 4. So negative 2, 4 is a point on my graph. Let's change colors here. I like the pink. If x is negative 1, I've got 1/2 to the negative 1 power, flip it over, which is 2. So negative 1, 2 is a point. When x is 0, I've got 1/2 to the 0 power, and anything to the 0 power is 1. So 0, 1. Now, when x is 1, I've got 1/2 to the 1 power, which is 1/2. So let's graph 1, 1/2. And when x is 2, I've got 1/2 squared, which is 1/4. And so this is getting really tough to graph way down there. There we go. And you can see that this is similar to our graph of y equals 2 to the x power, but it is aimed in a different direction. Whoops, that was not very good drawing of a line for me. There we go. So there is our graph. And you'll notice once again, this is going to go off on the right. It is not going to cross the x-axis, but it's going to go very, very close to the x-axis. So here's something that we have noticed. When we have the equation y equals b to the x power, here's the deal. If b is greater than 1, our graph is going to look like this. And if b is between 0 and 1, it is going to look like this. Okay, so if you think about those two graphs that I just drew, one of those is what we call exponential growth, and the other one is what we call exponential decay. Exponential growth is when things are growing or getting larger exponentially, and exponential decay is when things are getting smaller exponentially. So if you think about the two different graphs that we had, you can look at the picture I have here of the red graph and the blue graph. The blue graph is exponential growth, and we said that this is where b is greater than 1. And exponential decay is where b is between 0 and 1. Now, b can never be 1. That then is not an exponential function. It'll just be a horizontal line, and that's no longer an exponential function. But we've got a new vocabulary word here for your graphs, and you'll have this in your graphing project for this chapter when you do exponential functions. And that is an asymptote. And here is how you spell that word. An asymptote is a line that the graph approaches as x or y increases in absolute value. And so here's what I want to show you. If you look, let me pull up a little pointer here. Let's get a pointer. There we go. Do you see how right here this graph is approaching the x-axis, but it never crosses the x-axis? And over here, this graph is approaching the x-axis, but it never crosses the x-axis. What we say in these examples is that the x-axis is an asymptote. And that's what we have written right here. So the x-axis is an asymptote. And you'll see in the little box below here, I've just summarized exactly what I've said. The next thing we're going to do is identify, by looking at an exponential function, whether it is a growth function or a decay function. It's going to be one or the other. So in our little box here, we have an example of how you can tell. So for the function y equals a times b to the x power, we need to look at a couple of things. First of all, a needs to be greater than 0. So if we look at where b is greater than 1, this is an exponential growth function. If b is between 0 and 1, it is an exponential decay function. All right, so in either case, when you want to find the y-intercept is the point 0, a, and the domain is all real numbers. You'll probably need this for your particular video project. And the asymptote is that x-axis, which is y equals 0. Now, tomorrow we're going to learn how to translate this function. It'll change what the asymptote is. The domain will not change. For exponential functions, the domain is always all real numbers. And the range is y is greater than 0. So in a basic exponential function, this is what's true. Now, if we go to the examples at the bottom of the page, and these examples are like page 439, numbers 18 to 25. Here is all you have to do with these. All you have to do is look at these functions, and you have to determine if this is growth or decay, and what the y-intercept is. So if we go to this first one in example A, our b value is 0.95. That is between 0 and 1, so this is decay. Now let's go back up here to the box. The y-intercept is the point 0, a. So our y-intercept is going to be the point 0, 12, because 12 is our a value in our example. So let's go over here to example B. First of all, the b value here is 2. 2 is greater than 1, so this is exponential growth. Our a value is 0.25. So our y-intercept is the point 0, 0.25. Now this particular screen shows you in the box how you can write a function for either exponential growth or exponential decay. So in the basic function y equals a b to the x, where b is greater than 1, the value b is actually the growth factor. And if b is between 0 and 1, b is the decay factor. So when we have growth, that means that we are increasing, and when we have decay, we are decreasing. Now we can actually write that factor using percentages that are given to us. So if we have a growth factor, our b right here is 1 plus r, where r is the percent of growth. Okay, so if the growth rate is 8%, this would be 1 plus 0.08, which gives you 1.08. So then it becomes more than 1. Now, with decay, the decay percentage is going to be negative. So when we say b equals, there we go, b equals 1 plus r, the r is going to be negative. So if I have a decay rate of 2%, here's what I would have. I would have 1 minus 0.02, because it's negative, decay is negative. Then I'm going to have b equals 0.98. So here's my basic function right here. A of t is the amount after t time periods. A is the initial amount that you have before the growth or decay. So you may have like a certain amount of milligrams of some particular compound before it undergoes radioactive decay. So 1 plus r is your rate of growth or decay. R is greater than 0 for growth. R is less than 0 for decay. And t is the number of time periods. And notice that t is like your x, and that is what makes it an exponential function. So we're going to go to the next slide here, and I'll show you how to do this. Okay, let's look at an exponential growth model. So you invested $1,000 in a savings account at the end of the 6th grade. The account pays 5% annual interest, which is fantastic. How much money will be in the account after 6 years? So we need to identify everything in our example. So first of all, our initial amount is A. So A equals $1,000, because that's what we're going to start with. Now, R is our rate of growth. Remember, we need this as a decimal, so this is 0.05. And T is the number of time periods, and that is going to be 6 years. So we're going to have T equals 6. So as we set up this example, we're going to have A of 6 equals 1,000 times 1 plus 0.05 raised to the 6th power. Let's simplify that. 1,000 times 1.05. So now notice your b is greater than 1, which makes it growth. To the 6th power, let's take a pause and put that in our calculator. And that is $1,340 approximately. Let's go ahead and take a look at our second example. Suppose you want to invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? So A is your initial amount, which is $500. R is your rate of growth, which is 3.5%, which is 0.035. And T is the amount of time periods, which is 5 years. So let's go put that all in a function. So we have A of 5 equals 500 times 1 plus 0.035 raised to the 5th power. Let's simplify that a little. 500 times 1.035 raised to the 5th power. Let's take a pause and put that in your calculator. And that is about $594.